This video will give 3 definitions of special kinds of rings. So the first definition is integral domain. So you have to start with a commutative ring R. So a commutative ring R is an integral domain if A times B equals 0 means that either A equals 0 or B equals 0 for all A and B in the ring. So when you multiply two numbers together and get 0, that means one of them has to be 0. So let's do some examples. Here are some integral domains. The integers are an integral domain. The integers have that property. You can look at polynomials with real coefficients. If you multiply two polynomials together and get 0, then one of the polynomials has to be 0. Also, you can do the integers adjoined the complex number I. So this is the set of everything of the form a plus bi. I is the square root of -1. I squared is -1, where a and b are integers. It's a subset of the complex numbers. That also is an integral domain. Let's do some things that are not integral domains, just to see the difference. Z6 is not an integral domain. Z6 is not an integral domain because I could have 2 times 3 equaling 0 in Z6. And 2 and 3 are not 0, so it's not an integral domain. N by n matrices with complex entries is not an integral domain because, first of all, this is not a commutative ring. So an integral domain must be commutative. The multiplication must be commutative. Not the case with matrices. Additionally, matrices do not satisfy the second property. I could have 2 non-zero matrices that multiply and give me the 0 matrix. So definitely not an integral domain. So the first definition, integral domain. The next definition, a ring R is a division ring if every non-zero A in the ring has a multiplicative inverse. A inverse such that A inverse A is A inverse, which is 1, the multiplicative identity. Our rings, by definition, have 1. So that's the definition of division ring. In a division ring, you could do division. So you could divide by A. So division is legal in a division ring. The ring may not be commutative, however. So let's do some examples. So here are some division rings. You can have the rational numbers, for example. You could divide by any non-zero rational number. Also, I'll let this fancy H denote the quaternions. The quaternions we saw in a previous video, they could be everything of the form A0 plus A1I plus A2J plus A3K, where A0, A1, A2, A3 are real numbers, and these I hat, J hat, K hats satisfy I hat squared is J hat squared, which is K hat squared, which is IJK. In this order, that's -1. This is a non-commutative ring, but it turns out that you can divide. Every element of this form has a multiplicative inverse. I'm not going to prove that in this video, but if you'd like, they work out the details in the text. They show you how to divide by any quaternion in the text, so you can look at that if you're interested. But there is another example of a division ring. Q, of course, is a commutative ring, but the quaternions are not. Here's an observation. Any commutative division ring is an integral domain. If you could divide here, it's easy to see why. If you have A times B equals 0, and you divide by A, so you do A inverse A times B is A inverse times 0. So I take A times B equals 0, I divide by A, I get B equals 0. So if you could divide, and it's a commutative ring, then you have an integral domain. Okay, so far in this video, we've defined integral domain and division ring. The main definition I've been trying to build to, this one's more important than the other two for sure, is field. So this is a main definition, you gotta know it. A field is a commutative division ring. So a field is a commutative division ring, therefore also an integral domain. So examples of fields are the rationals, the reals, the complex. You could even do Z mod P, but P has to be prime. If P is not prime, then you may not have an integral domain, as we saw in this previous example. So I know we have three new definitions: integral domain, division ring, and field. Field is probably the most familiar to you based on knowing these examples. But I'd like to draw a Venn diagram to kind of help organize what's going on with these three new definitions. So here is a Venn diagram. This big set denotes all the rings in our course. And in our course, our rings are defined to have unity. So there's a multiplicative identity number 1 in the ring. In here we have commutative rings. Commutative rings are where the multiplication is commutative. And as a subset of commutative rings, we have integral domains. Division rings may or may not be commutative. So this set over here of division rings may intersect with commutative rings. And the intersection, fields. So let me fill in a few elements in each one of these sets. Matrices, n by n matrices over the complex, that's a ring. It has an identity, multiplicative identity, but it's not commutative. It's not a division ring. Commutative rings, we've seen, are like Zn, where Zn is not prime. So that's a good example of a commutative ring that's not an integral domain. So integral domains could be like Zi, it could be Z, it could be polynomials. Those are examples of integral domains that are not fields. Division rings, a non-commutative example of a division ring could be the quaternions, which I denoted with H. And then fields, the most important set of rings for our class, could be Q, Z mod P, P has to be prime, complex, and reals. As we go along in our course, we'll see even more examples of fields that we haven't seen in our past as well. All right, great.